Welcome to this determination of roots of algebraic and transcendental equations. So here we'll be talking about finding the roots, and there are few methods which we will discuss here. One is the bisection method, another one is fixed pivot iteration method, then Newton-Raphson method, and the secant method. So these four methods will be discussed, and let's hope if we can cover at least one or two today. So the bisection is very easy, as the name suggests, bisect. Yeah, so intersect into two portion. It's something like this. So it is based on the following theorem of zeros of continuous function, and which you are familiar with. So given a continuous function f a b to r such that fa into fb is less than 0, right? Fa into fb is less than 0. So if it is a, it is b. So it is taking positive and negative value at a and b. Therefore, this product is less than 1. Then there is definitely a root, yeah, alpha. There is a alpha there, which such that f alpha is equal to 0, right? So it's clear to all of you. I think you know this theorem. And the outline of this algorithm of the bisection method. So it's not a very, something involved method which I need to explain. It is very easy and kind of algorithm which I am giving you here. That should be enough. So you choose that interval first, where you find that there is a root. Yeah, so that's the kind of your initial guess for the interval. That okay, well, one of the roots of this equation will be in this interval a to b, because fa into fb is less than 1. We are sure that there is a root. There is at least one root. That's what we are sure here. So we'll go with that interval, and then we will actually bisect that interval. How? The bisector method, this bisection method will generate a sequence of the interval. So this is, for instance, you have A0, B0, the beginning one. Then you have A1. So I1 interval will be something A1, which we are denoting here, and B1. How to get this A and B now for the next interval, the lower boundary and the upper boundary? First of all, those interval, the size of interval will reduce, and indeed it will be half, with the property that the product of always with the boundary values here fa and fb is going to be less than 0. So how to get these, how to update these new values of the boundaries of the interval? That is actually the algorithm here. So what we do, we start with the initial one, a and b, and let's store in a0 and b0. That's the initial given interval, or whatever you have guessed that interval. So these are the boundaries first for that interval. So I0, which we are calling. Then you compute the middle point. Yeah, that is what the bisect name comes. You compute the middle point of that interval. Yeah, just the middle of that interval, and say x naught. This is basically your, the first approximation to the root. Then you proceed. Then you check whether f, so the left boundary, the middle point, whether this is going to be less than 0, or if this is the case, then you set your boundary, the left boundary to this ak, the right boundary to that x. If it is other way around, that fxk bk is less than 1, then you set your boundaries here, that the left boundary is your xk, the right boundary is your bk, and then go again to the middle of this interval and continue the same story again and again until you get the value which is close to the root. So maybe just first geometrical interpretation, then if you have any query you can ask at that time. So suppose this is your function fx, and we have initial values for the interval a and b, and fa into fb will be less than 1, and we are sure that there is a root somewhere in between. So what you do, this is your initial interval, then you compute the middle point of this interval and see whether where your root lies. How to check where whether your root lies here or your root lies in the second half, in the first half or the second half. So in this case, naturally the second half, then fx0 and fb will be negative. In that case, the product of this, then this is your desired interval, the next one. Then again you make half of it and then again check. So in this case, the left portion where your root lies and that product will be negative again. Then you go for, this is your I2 interval, then this is your middle, then your I3 interval, and so that the length of the interval is getting reduced where your root lies. So naturally, after some time, you will see that you are pretty close to the root. So the algorithm is, I think, pretty clear to all of you, isn't it? There is no mathematics behind or anything here hidden.
Yes, sir.
Very good.
Excuse
Yeah,
me,
so
sir.
this is the situation. Any question?
Suppose, sir, we have 2 or more roots in that interval, then which root it will predict?
Yeah, so here the algorithm, now we are considering that you have a root, you have one root, you have started with such an interval where there is only one root. Yeah, and then we are explaining everything. So first you have to make sure that, okay, in this interval, yeah, there can be two roots, and it may happen that again when you started with I0 and then in I1 the left portion also has a root and the right portion also has a root, because you have this situation. For instance, you started with something like this interval from here to here, and there were many roots here. There were three roots, right? There were three roots, and then you made a half of that interval, and still you see there are two roots. So that you have to, then you go in each of the interval. So in the left also you have a root, right also you have root. Separately you run your algorithm for this and you run for that. Yeah. So the idea is that you can do that. Huh?
Sir, but if on one side we have two roots and this side, if we do FA and FB and then we multiply them, the product would be positive in that case, in case of this side with two roots.
Yeah, so it will go to that root only.
Yes, sir.
Then your algorithm will check that, okay, it will not recognize that there is a root here.
Yes,
Because
sir,
here it is negative, here also negative, so it will say that this is positive, product is positive. It will move to the second half. Then you have to change the width in that case. If you want to identify those, you have to compute those also. So the point is, as I said at the very beginning, that we are explaining here, in fact in all our examples also, we will first make sure that in this interval there is a root, one root, and then we will go forward with this bisection method. Fine.
Sir, what if there are odd number of roots between A and B?
If
Means suppose there are three roots between A and B, then will this method still work? Means it
yeah,
is not
that's what I explained. There were three roots here, right? There is so in this interval from here to here, let's say, if you have taken this one, first of all, as I said, it's the algorithm will work when you have exactly one. But for suppose you have taken this, algorithm will still work. So FAFB is less than one. Fine, there is at least one root. We know this. Then you have made half of this, so you are somewhere here. Yeah. Now you have the left interval and you have the right interval. It will not recognize for the left one, because here it's negative, here it is negative. So it will have like positive here, and that product will be negative there. So it will move to this root. So finally you will get this root. So you will get one definitely in that interval.
okay, sir.
Yeah. So suppose this was the root and we have explained that then it is going close to alpha. The beauty of this method is, though it is very simple, and there are some reasons not to use this also that we will mention later on, and there are reasons to use this method, that is also true. Why what are the reasons that we can always use this? Because of the convergence part, that you don't need to worry about the convergence, whether method will converge or it may not converge. It will definitely converge to a root, that is clear. Once you have FAFB is negative, once you have FAFB negative and you make sure that there is a root in between, definitely it will go to some root. It will converge to the root of the problem. That is clear. It can never happen that it is not converging. It will converge. The reason is clear, which you have also seen here, because basically what you are doing, you are reducing the length of your interval, nothing else. Making a smaller length, and again make sure that where is that root. Out of sudden this will not disappear, right? If initially FAFB is negative and then you made a half point and then again you will check, definitely it will be within or at the boundary of the interval. So you will never lose that root. It will be there, and every step you are reducing the width by half of your interval. So definitely it will converge. There is no point that this will not converge. It's not like Gauss-Seidel or Jacobi we were talking about, that sometimes it may not converge. It will always converge. So this is, I think we can forget this proof in fact, which is a mathematical way of doing what I explained you, that it will always converge. Like this is the initial.
So can it happen that the exact root is found out in a finite number of steps? Like
Yeah, if your interval falls exactly on the root when you are dividing that, right? When you are dividing your interval, then the middle point, if it is already, so if this is the middle point and then it falls there, so you are done. You got the exact value.
So I think
so
if
I would
roots
The
are
value of the
rational,
function is
then
equal
it
to 0
will.
at that point.
Eh?
So
If roots are rational, then there is chance. If irrational, then it will not happen. Has
If
to
there is,
convert.
if there
If
are,
if a root is rational, then that possibility may happen.
yeah,
That we exactly.
correct. So the if middle point falls on the root itself, you have that possibility that it exactly, hit the root. Otherwise, no. So here f alpha is 0, that is the root. So this is the interval width we are denoting by this ik, the difference upper boundary minus lower boundary. So what you have noticed here, that ik is always, the length of ik is half of the ik minus 1, correct, of the previous one. The length of the interval is reducing by half, clear? So out of this iteration, you can conclude that ik, the length is just I naught by 2 power k. Yeah, this is start with I1, so the half of so the I1 means after one iteration, so the length will be I naught by 2. Then you go with I2, that is half of I1, and I1 is again I naught by 2, so 2 power 2. So this, in this way you can conclude that this ik is I naught over 2 power k, and I naught is nothing but b minus a, the initial one. So we have the length here of ik given by b minus a over 2 power k. Now if you denote the error by xk minus x, then your error here ek is less than ik by 2. Why this relation? Can someone tell me? Why ek is less than ik by 2? See, you have this alpha, for instance, there. What is I naught? I naught is this whole interval. I naught is the whole interval. You have this alpha here. Your
Sir, xk minus alpha is only a part of the entire ik length.
yeah, yes,
So
yes.
that's why it is always less than half of it.
Less than half. So it will be somewhere there, like in this case, the exact root is here. So, and this is the middle point, x naught, the first approximation is the middle of that. So wherever it is, whether it is here, whether alpha is here, whether alpha is there, definitely that alpha minus this x naught, that will be less than the width, half of the width of the interval. Correct? That's what we have written this. Ik, we know that relation there. Yeah.
Sir, why it cannot be equal to half of ik?
When your root is sitting exactly at A and B, if your root are sitting at A and B, why you will try to compute? You started with that FA into FB is less than 0. From this point you have started your algorithm, right? That means root is not at A and B, root is somewhere in between. And if it is somewhere in between and x naught is in the middle, if your root is here also, it will not be half, right? It will be less than half. That difference. And did you follow?
Yes, sir.
X naught is middle exactly of the interval, right? So for example, your actual root is here. So this width is just this one. If your root is here, your width is, sorry, this error is this one. That will be always less than half of the whole width. True?
Yes, sir. Since k is always in the middle of that interval,
Yes.
so any interval in between that will be
So it will be
smaller
less
than the.
than, strictly less than. True. So then ik relation we have already, we have kept here. So as k approaches to infinity, your ek will go to 0. Clear? So definitely the error will go to 0 in infinitely many steps for sure. So this is the very kind of mathematical proof which you hardly need. You can understand from the algorithm itself that it will converge. So the bisection method is globally, we can globally converge it. Means always there is no restriction. There is no restriction on anything for the convergence. Yeah. Unlike Gauss-Seidel, we have some restrictions and so on, and there will be many other methods which follow now. They will have some restrictions, but not this one. This bisection method has no restriction.
So, but here that the condition that FAFB is less than 0 has to be fulfilled. So, what if the graph is like just touches the x-axis and goes up? Like in that case, FAFB will never get equal to 0. Sorry, less than 0.
Yeah, but you will
So
start only then when there is a FA into FB is less than 0. You will start only this then only that there is a root in between. That is a condition from the beginning itself. That if FA into FB is less than 0, that means there is a root between alpha is between A and B. After that only we are talking about that root.
okay.
So for example, here now find the smallest positive root of this equation, and 5 iterations we want to have here. So the actual root, if you just look at the scenario, you have these so many roots. You have 2.1, you have minus 2.33, you have 2.0 and so on. So smallest positive means we want to get this 0.20 basically. So we realize that, okay, F0 is 1 and F1 is minus 3. Obviously, your questions which will definitely come, that how to choose that how to confirm that 0 between 0 and 1 is only one root, and that is the smallest positive is definitely because you have started with 0, so it's more than 0, and but where to end exactly, that is the question. If 2 false there, it may lead to something else, and so on. 3 false. So those questions will still remain, but anyway, not in this question, in this problem, of course. So you have the f0 is 1 and f1 is -3 in this case. So there is a root between 0 and 1. So your initial interval is 0. The upper boundary is 1. That is initialization we call. Then you compute your first or the 0th approximation, whatever you call here. Usually we call that the 0th approximation. Yeah, the first one. So 1 plus 0, the 0.5. You start with this 0.5. Then you check that where it lies now, whether f(a)x0 is less than infinity, less than 0, and or the other one. And then you will define your interval wherever your root lies. So situation is like this. You started with 0 and 1. You have 0.5, the first middle point, and then you realize that actually it's in the left hand side, right? A0 and x, the product is less than 0. So your new boundaries will be left boundary and the right boundary. Yeah, the left boundary and the right boundary will be, left boundary will be a0, the right boundary will be x0 of your new interval. So 0 is the new boundary, then 0.5 the upper boundary, the lower boundary is 0, the upper boundary is 0.5 because of that reason, right? Because of this reason. And then again you go with the middle one. So this is your x1, correct? This is your x1, 0.25. And here the value is negative of your function, it's negative. So negative positive, again it is moving to the left one. Again it is moving to the 0.25, the new boundaries. So the left boundary is 0, the right boundary 0.25, and the middle one 0.125. So now you see here positive, positive, there is negative. That means now we are moving to the right boundary there. So you will go with 0.125 your left boundary and the 0.25 your right boundary. And then this is the middle one. Again, you check your function value. It's positive. So here positive, negative. So it is moving to this portion now. So you go with that 0.1875. Then you have 0.25. And then the middle again is your x4, so 0.2185. That is the answer after this four iterations. Correct. So root lies between this and this number, and then you can just make a half of it. So that's after 5 iterations, x5. Is that fine? Simple. It's pretty simple. Only you have to evaluate that f to see where it lies. Clear or any doubt? No doubt. So we can move.
Yes, sir.
Yes, sir.
Okay, very nice. So fixed point iteration method, that is the next one, because the first one was too easy actually. Now we are moving further. Fixed point iteration method. Idea of general iteration method. Rewrite fx equal to 0 to the form x is equal to gx. Yeah. So this is your given equation where you want to find the root. This is now similar to what we have done in this iterative methods there in Gauss-Jacobi and Gauss-Seidel. This is similar. So fx equal to 0. This is the equation, given equation, polynomial form or whatever. You write down that in the form x is equal to gx. Yeah, left hand side you take x and the right you take, get to the right hand side out of this equation. And then you set up the iterations, a similar idea. You set up the iterations here, xk plus 1 and their right hand side gxk. and then k0, 1, 2, 3, and so on. So x0 you need, and then x1 you can get, and so on. So again, initial guess is required in all iterative schemes, including this one, of course. So the convergence, but now the problem is here, the convergence of the method will depend on this G. How you distribute this, how you split. There also splitting was important. The convergence depends on the splitting. Gauss-Seidel is different, Gauss-Jacobi is different, and they act differently for different problem. Sometimes one is convergent, other one is divergent, other one is convergent, the first one is divergent, and so on. So here also that splitting is important. How do you split this fx equal to 0 in this form? And then the convergence will depend exactly on G here. And just a remark why we call fixed point iteration method here. This is a general definition for the fixed point we use in analysis. The point x star is called a fixed point of the function G if x star is G x star. That is called the fixed point of G. The x star is called the fixed point of G if x star is coming to be Gx star. That's a definition of the fixed point, and this is based on such a criteria that fx equal to 0 you are splitting into x is equal to fx. So x is a fixed point, right, of G. X is a fixed point of G. Fixed point of G. Therefore, this idea is coming up, and here we have set up the iterations, and as usual, so obviously you will pass the initial guess. You will not expect that you will get exactly same output. You will get some other value, then that value will pass, you will get some other value, and so on. But this process will converge, not always, but under certain conditions on G, which we will also discuss. Fine. Okay. Yeah, anything? No. Good. So we have fx equal to 0. We have rewritten to x is equal to gx in the fixed point form. Not that G is not unique, right? That is clear, right? You will write in some other form x equal to gx. I will write it something else. Your friend will may write something else. So G is obviously not unique when fx equal to 0 is given. A different person can have a different G. For just an example here, we take gx is equal to x minus fx, right? Gx we will take, so we have x is equal to gx, and gx I have taken fx x minus fx. So basically I have fx equal to 0, right? The same equation which we are supposed to have. So you can have several splitting. You can have gx as x plus 2fx. Again, you will get the same notion. You can get gx in this form. I mean, there are several. I mean, we will see in the examples also. There are many possibilities which you can have. In fact, I would say infinitely many ways of writing this fx equal to 0 to x is equal to gx.
But also splitting will not lead to convergence.
Sorry?
So for the convergent G, that will be unique. Like the G that we choose to convert.
No. That will not be also unique. Yeah, that will also not be unique. That only this G will give you the convergence. No. Again, there could be several G's which can lead to the convergence. Fine. So sufficient condition. What is the sufficient condition? So from here you will get the idea that if G is continuous, that is the first point, of course. It's not tough. Always in interval that contains the root. Second is this. This is the important condition. Yeah, you want to ask something? Do you have any question? Okay, no. So the condition is this one, that the derivative of gx should be less than 1, strictly less than 1. There we had the condition of eigenvalues, right? here we have on derivative, that derivative of g should be less than 1 in that interval which contains the root. And then for any choice you take in that interval, the sequence will converge to the root. That is the sufficient. Again, this is sufficient condition. Yeah, don't confuse with that. That if you don't do this, then it will diverge. No. If you do this, it will converge. That is the surety we have from this result. Clear?
But
So the
if
result
this
is
method fails, we can say convergent or not, right?
in.
If g dash x is greater than 1, then we can't comment anything.
Then we cannot comment anything. Yeah, absolutely. Then we cannot comment because it's a sufficient condition. We don't know, greater than 1 also it can converge, it may not converge. Here we don't have necessary sufficient condition. That is the problem. We have only sufficient condition. It's very good to have necessary and sufficient condition because then everything is clear. But only sufficient condition is good because once, yeah.
So what is rho here?
Rho is nothing. What we are telling, actually, that g prime should be strictly less than 1. See, g prime x will be something, right, out in this interval, AB interval. So that g
So
prime
maximum
x
value of g prime
is,
in this.
yeah, is less than something which is less than 1. The point is that
Yes.
this should be strictly less than 1, right?
Yes, sir.
So instead of that, you can also say that this g prime x should be strictly less than 1. That's all. The meaning is this one. Okay. So we start with that x k plus 1 minus x, that is our error, right? X star is the actual solution. For instance, gxk plus 1 is gxk, our scheme. X star is gx star, that's the actual value. Okay, so we have, this is if you still remember something, Lagrange mean value theorem, or you forgot? Yeah, Lagrange mean value theorem, you remember from the previous semester?
Yes, sir.
Yes, sir. Yes.
Yeah.
Yes,
sir.
sir.
Yes, sir.
So I applied that only, gxk minus gx star divided by xk minus x star is equal to, there will be some point in between xi and so on, right? You remember? Okay.
Yes,
This
sir.
is exactly that result, the Lagrange mean value theorem. And okay, this is just Lagrange mean value theorem. So since g prime x is bounded by some rho, whatever, I mean, this is will ease the proof here by taking rho. That was the reason it is given there also. So that means that you have this error here, xk plus 1 minus x star less than rho and xk minus x star, meaning rho square xk minus 1 x star and so on. If you go, that is the initial error. So this error at k plus 1 x star is bounded by this rho power k and the initial error. Now if k goes to 0, k goes to infinity and rho is less than 1, what will happen? This error will go to 0. The error will go to 0. This will go to 0. So this is the proof of the convergence, which is just the sufficient condition that if this happens, definitely it will converge. It does not tell anything that if this g prime is greater than 1, what will happen. That this theorem is not claiming anything on that. Is
Excuse me,
that
sir.
clear?
Hello.
Yeah, is it fine? Any question? Yeah.
Yes, sir. The function should also be differentiable in that interval, as you
Yeah.
use that.
Yeah. Yes. The function should be also differentiable. True. Otherwise, this g prime, I mean, you will not get the g prime basically. Yeah. So just writing that this condition itself is saying that it is the derivative exists. Huh? Yeah, that's fine. Okay, the geometrical interpretation. So we have this scheme xk plus 1 is equal to gxk, correct? Suppose this is y is equal to x line, and then you have here y is equal to gx, the curve of this gx. So two curve, y is equal to x and y is equal to gx. There are two curves here. You start with this, some initial guess, correct? You will start with some initial guess. Where is the root in this line, in this figure? Where is the root?
Intersection of two
The
curves.
actual root, right? The actual root is this one, correct? This is what we call alpha or x star, whatever. So we start with some initial guess. Let's say it's here, x naught. Then what will be the first approximation? That will be given by g, right? So gx naught. What is gx naught? It's something here. So gx naught. This is your gx naught, which is your x1. So on this x-axis, where is x1? X1 is here, right? So this is your x1. Now on this x1, your gx1, that is your x2. You have x2. And where is x2? X2 is here now. Now you go move further and further and further x3. So x3 is getting closer to the actual root now, or x4 or whatever. So in this way you are approaching. X0 was here, the far from here. Then it is going to x1, that is going x2, then x3 and so on. After some time you will see it will approach to this one.
Sir, in this case also, if we have multiple roots, then we can say which one will become.
Yeah, the same problem. In all these methods, Newton Raphson, this, that. So when you have multiple roots, you are not sure that exactly to which route it will go. So
Then
like
we will
here,
change the interval to find out the other roots.
yeah.
Sir, can we say that x0 and x1 will be always on different sides of the root and similar for all other iterations?
In this case, I don't know,
Or it
depending
depends
on
on
the,
nature of gx.
yeah, it depends on gx, right? Exactly. So in this figure, like you see, that's a fluctuating around this because of the nature of g. But I don't think that this is going to happen always.
Okay,
If
sir.
G graph is something very, different, then it may again fall to the same side.
Okay, sir.
So here you have, we rewrite, for instance, x cube minus 5x plus 1. I think the same example which I had taken there. So rewrite the equation as x is equal to gx in this form. This is one way of writing. Yeah, out of this, what I have 5x one side and x cube plus 1 other side. And then out of this, x is equal to x cube plus 1 over 5. This splitting I have done. This splitting I have done. Now iteration methods, you can immediately write your iteration method. And you can see that g prime is 2x cube by 5. And if you take the interval 0 to 1, yeah, 0 to 1, your g prime is less than 1, right? In 0 to 1, your g prime is less than 1. So we take
For the screen
Well, your
sharing
screen
stopped.
has stopped
Suddenly.
sharing.
Yes, the whiteboard was being shared in between.
what?
So the screen is not visible.
There's not
Screen. Oh,
whiteboard. So your screen sharing stopped. Can you share again?
oh, okay. But here I did not realize, and I did not do anything actually. Okay.
Someone else did.
Sharing the whiteboard, I
The
think.
mistake it
That
happened for me. I did not do it intentionally.
Oh,
Some option appeared and I just clicked randomly anything and it got stopped.
okay. Yeah, some technical. Now it's fine. Can you
Yes,
see now?
yes, sir, you can.
Okay. So we were here. This was done. Yeah. So we were here, right? In the
yes, sir.
example. So we have this example we rewrite to this form. How this form is written, that I think I have explained, right? So you have 5x is equal to 1 plus x cube, and x is equal to, this is one way of writing, yeah, not the only way. So from there but we realize that g prime x is 3x square by 5, and if our interval is 0 to 1, then this g prime is less than 1, and we can take any guess in between. So we have taken 0.5 as initial guess, and then x1 you will compute x2 and so on, and you can see this kind of convergence, right? That the value is converging. Good. Okay. So if I take initial guess 2.5, for example, in this above problem, 2.5. So the 2.5, there is a risk because you have here 3 by 5 and x square. Now you have taken initial guess where this g prime x is more than 1. So we don't know, we are not sure whether it will converge or not. So we try, and actually it is not converging. That is true. Note that g prime, yeah, the g prime is 3x square in above both the cases. So we have same splitting. But in case 1, g prime was less than 1 and the convergence was guaranteed. In the case 2, g prime was greater than 1, hence the convergence is not guaranteed. Yeah, it's not guaranteed. I'm just using word not guaranteed. It was not like g prime 1 greater than 1, so it will diverge. This is not the statement I'm making here. The convergence is not guaranteed in the second case, and it happens that actually, yeah, it was not convergent. The iterations diverges towards plus infinity. Another splitting I can do, for instance, x is equal to minus 1 over x square plus 5. In this case, if I take the root 2.5, initial root 2.5, what will happen? Let's just check. Yes, I'm converging. I'm converging in this case by taking this x naught is equal to 2.5. And what happening in this case, if you check also that what is g prime, the g prime is greater than 1. G prime is greater than 1. But the convergence is still there. So this is exactly what I tried to explain you there, that it's a sufficient condition, not the necessary condition. It is a sufficient condition, not the necessary condition. In this case, the condition was not satisfied and still we have convergence. The conclusion is that bisection method is an iterative approach that narrow down an interval that contains a root of the fx, and convergence is always guaranteed. Whereas in the fixed pivot method, you have to write down your fx equal to 0 equation in this form, x is equal to gx, and the convergence will be guaranteed if this g prime x is strictly less than 1. That is the conclusion out of these two methods. In the next method, what we will continue with the Newton-Raphson and the secant method. I think it will not take more than 1 hour, and we will be done on Monday itself. So Monday we'll finish this portion. So I think it's time for you to go to the other class, and you can leave.
Sir, one question.
Your voice is on and off, so I cannot.
Audible?
I'm audible, sir.
Now it's better.
Have you posted this on MS Teams, sir?